So our very last keynote will continue to look to the future. Um, sorry. Uh, Mr. Shen, Program Manager at the U.S. Defense Advanced Research Projects Agency, DARPA, will speak about the future of conflict in the information space by covering DARPA's research on their game-changing technology and science. Shen, the floor is yours.
Thanks. All right. Well, I hope you guys enjoyed the last panel. I am the last thing between you guys and airplanes and lunch and everything else, so hopefully you find this engaging and an interesting talk. So I wanted to talk to you a little bit today about research that we're doing in cyber defense, a strategy that we call Win at Cyber, largely because it stems from work that we've been doing in the last couple of years to think very specifically about the technological challenges of how we will solve the cyber defense problem in the next 20 years. What are the technological barriers for us to be able to build protected systems in cyber? Now, before I get into the details of this strategy, I thought that I would introduce our organization for you so that you know who DARPA is. Probably many of you know about us through some means or another, but probably you don't know that much about the details of the day-to-day work that we do. So DARPA is founded on a single event. A lot like other agencies, we have this one founding event in 1957, October 4th. This day is when this satellite was launched into space. This is Sputnik. It's a radio transmitter with a sphere that's about 23 inches wide. And that particular event created what we call technological surprise. By 1957 standards, the radio that was inside of Sputnik was nothing special. The sphere was nothing special. But the fact that the Soviets were able to push this satellite into orbit with rockets meant that they could probably also deliver nuclear weapons to the United States. And that was, in and of itself, a very important event for our country. So in 1957, what we didn't realize was that the Soviets had this technological capability. That's a failure of intelligence. What we really didn't realize was how they had done this. And that's what actual technological surprise is. So we didn't know ourselves how they were able to achieve this goal of shooting a rocket into space. And so what happened in 1958, 4 months later, was that Eisenhower issued this decree that said we should never be surprised again technologically as a nation. And this document is the founding document of DARPA. It says we'll create a research agency within the Department of Defense. It is a matter of national security that we understand technological surprise and that we invest in research to be able to prevent that technological surprise. So this is probably not how you know DARPA as an organization. I'm sure most of you have not read DoD Directive 5105.15. That's not how you know about DARPA. But you probably do know about DARPA from things like this. This is a cartoon from the 1990s called The Teenage Mutant Ninja Turtles. And in Volume 2, Issue number 10, The Descent into DARPA is what it's called. The depiction of DARPA in this particular cartoon is interesting. Apparently, we are evil scientists, all of us. We create psychic powers, and our goal is to control mutants. Well, that's not quite what we do. What we do instead is build neural control systems, things that understand thoughts for the purposes of controlling machines. So this is a prototype of a system that we built a couple years ago. A system that reads the signals of your nerves in your arm, or what's left of your arm in this case. This person has lost an arm to a war injury, and translates those signals into digital signals of movement for a robotic arm. So we don't do mutant control, but we do build cyborg systems and control machines. Now, maybe you don't know us from that, but you know us from this. This is a 2014 movie starring Adam Sandler, where aliens have come down from space, and those aliens are attacking the planet, and it's up to DARPA to defend the world. Apparently, the way that we're going to defend the world is we're going to build a laser cannon that kills 1970s video game characters, which is the form that these aliens take when they come down from space. And this is how we're going to do it, and we're going to arm these two idiots to go do this amazing task. Actually, this is also not quite true, but it's a lot closer to reality. So the first lasers were actually developed out of a DARPA program. They were designed to kill missiles in a program called Seesaw, and later in a follow-on program called HELADS in the last couple of years. These high-energy lasers are designed to kill missiles so that aircraft could be protected from missiles that are incoming. Okay, so the facts of DARPA as an organization are a little bit more simple. We're a research funding organization within the Defense Department. We were asked to prevent technological surprise, and we do so through undirected research from program managers. So DARPA is a really small organization. We're about 80 people. At any time, we can get up to about 100, controlling about $2.7 billion worth of research budget in the form of somewhere between 200 and 300 programs at any one point in time. So every program manager manages 2 to 3 programs at any point in time. And those programs fund researchers from university and industry across the world. And the idea is that program managers are term limited. They can only come to DARPA for somewhere between 3 and 5 years, and they have to leave because they're stale at that point. They don't have any new ideas. They have to go away, think about other problems, and come back. And right now we fund work in machine learning and hypersonic flight and cybersecurity, which is what we're going to talk about later today, in brain-computer interfaces, et cetera. Now, what I think is interesting, these are the facts of what DARPA is, but actually what I think is interesting about DARPA is not these facts, but some really basic things like a program called Falcon that was launched a couple years ago. So DARPA is an agency that is designed around failure. And this particular program you can think of as the quintessential example of failure. The goal of this program was to fly a plane at Mach 20. Okay, so just to give you an idea of what Mach 20 is, Mach 20 is about 10 times faster than any plane flies today. In order to do this, we built a plane, and we launched it from space. And the reason that you have to launch a plane like this from space is that if you launch it from the ground and try to go Mach 20, your wings burn up. Okay, there's too much air resistance and heat caused by that process. So this program flew 2 planes, both of which burned up. One plane flew for 9 minutes from space and then destroyed itself, never reaching Mach 20. The second plane flew for 3 minutes at Mach 20. Okay, this was a $60+ million program that flew for exactly 3 minutes at Mach 20. But what's interesting for us, and it also blew up over the coast of Alaska, what's interesting for us is that that failure actually taught us all sorts of interesting things that we could not have learned by just looking at the theory of hypersonic flight. We learned all of the operating characteristics of how to build wings. We learned all of the operating characteristics of how to launch these planes to begin with. And in the future, this kind of work will eventually lead to systems that can fly at those kinds of speeds. Now, the first 50 years of DARPA have resulted in all sorts of technologies, many things that you know about ubiquitously today. The first rocket that took human beings into orbit, the first mouse and graphical user interface were invented out of a DARPA program. The internet, you just heard about the internet, was originally called the ARPANET, which is the original name of DARPA as an organization. GPS, Siri, all of these things were invented out of DARPA programs and DARPA funding. But you know, the thing about all of these efforts, even though they're entirely ubiquitous, these efforts were all centered around a military application to begin with. So that internet that you're using to watch cat videos, that internet was originally designed to be a survivable command and control system for nuclear weapons. Right? That was its original intent. It was a network of networks that could survive. So the first 50 years of us as an organization has been spent a lot thinking about military applications, and specifically thinking about how we can fight better on land, in air, in space, and in the sea. And what's happened in the last couple of years is that more and more of our fight has become information-based. More and more of what we care about is the space of information and cyber. And in this space, the warfighting problems that we deal with are fundamentally different than the problems that we dealt with in the past. And so I think it's worthwhile decomposing the problem of fighting in these domains so that you understand why cyber is fundamentally, and cyber and information are fundamentally a different problem. For one thing, this modality of fighting is fundamentally asymmetric, right? Low-cost attacks can be actuated against millions and millions of people on a global scale very, very quickly. And if you think about what that means and what that implies, it implies that we need response and control over a system that operates on microsecond time frames or millisecond or nanosecond time frames. And that means that we need to be able to react faster than human beings can possibly react. And so what we've been thinking about over the last couple of years is a strategy to do exactly that. How can we build systems that, one, either don't need reaction at all because they're impervious to attack, or two, that can react so fast that they can react on the time scale of automated attacks? And we call this strategy Win at Cyber because the idea is that in 20 years we should have the technological capabilities, not necessarily the policy, right? That's what you guys are here to talk about, but the technological capabilities that are available to policymakers to think about how they would actually do this. So there are four main thrusts in our cyber research, one of which is what we call building unhackable systems. How can we prevent attacks from actually causing damage? How can we build systems that assure the properties of security that we need, and in such a way that it's practical to actually build them? Now, that works for systems that you're going to construct anew, because fundamentally you need to construct those systems in a different way. But there are systems that we have that are legacy systems, systems that have an already sunk investment. And for those systems, we think about how we're going to build autonomous systems that can respond to cyber on machine scale timeframes. And to do that, we think that we need to build capabilities to automatically detect attacks, to operate through attacks when attacks are actually actuated, and most importantly, systems that can find those attacks and patch themselves over time so that they are no longer vulnerable to that class of attack that they have seen in the past. So what I'm going to do here is give you some programs. There's many other programs in our office, but to give you a sampling of programs in each of these technical areas so you have a sense of what this office that we're at, I2O, is trying to do. So the first of these is a program that is designed to build reliable military systems that are inherently unhackable. And the idea here is that at the end of the day, programs are math, and math can be proved. Now, the problem with programs is that they're really, really hard to prove. And typically, the effort required to prove those programs is worse than the actual effort of writing those programs. So it's been not practical to build systems that are fundamentally secure. So the Hack'ems program has been about how do we build tools that help people build provable systems from the outset with relatively low effort. And we do this with a combination of tools from automated theorem proving and from automated code synthesis, coupled together to construct very large-scale, provable systems that have properties that are verifiable. Now, one of the things that you can do with these systems is what we call cyber retrofit. So the idea here is you take a very large military system that already exists, and you replace key components of that system by verifying those components that they assure certain kinds of properties. If you do that and then assure that the whole system, which has some set of trusted and untrusted components, can operate together and assure the overall properties of the system, you can build a system that looks like this. So this is the unmanned little bird. It's a helicopter. It's an unmanned helicopter. And what you're seeing here is a landing of this particular helicopter, which is not that exciting, except that it's not clear from these pictures that this particular helicopter is actually undergoing an attack of its untrusted systems while it's trying to land. Now, that attack, it was conveyed by a USB device plugged into its flight data recorder, and it was designed to jump from that flight data recorder onto the flight control system and take over the flight control system, causing the helicopter to crash. So what you would have seen, had I shown you something exciting, was a crash. But actually, the whole point is to avoid anything exciting. So it's boring, but it's exactly what you want. Now, that's a class of solution that you can build if you're building new software. But what if you have software that already exists? You can't do that. So we have programs in our office that are centered around being able to detect attacks automatically. And I'll focus on one program that's doing this at massive scale, a program that's called Network Defense. And the idea behind the Network Defense program is that we're going to use machine learning tools to learn the pattern of traffic behavior on networks attempting to connect to our protected systems. And the idea is that we want to protect an entire enterprise, a system that's sort of nation-state scale in terms of the number of systems and in terms of the network footprint. And what we do is we build a model of all of the hosts in that system and all of the hosts that try to communicate with that system so that we can detect anomalies when attacks are actually being actuated, either on individual systems like this, which you can see an anomaly here that our system can detect in real time, or in a coordinated attack across multiple systems or from multiple systems on multiple servers. And the idea here is that you need to be able to run these machine learning analytics at massive scale. Typically, an enterprise like this has on the order of 89 billion communications a day. This is a subset of the DoD network, actually. And so being able to, one, build the model of normalcy, and two, be able to run the detection of anomaly at massive scales is a key challenge for these kinds of systems. Network Defense is in its last year, and it's actually deploying these systems to both the DoD and to commercial networks that need protection. Okay, so sometimes you can detect these attacks, and if you can detect these attacks, it means that you might be able to do something to mitigate these attacks. That's sort of first-order autonomy. And so what we want to do in the next class of programs is think about how we might operate through attacks that we can detect automatically. So how do we couple detection with some kind of strategy for mitigation in an optimal way? So first I'm going to tell you about a program called EdgeCT. Now, the interesting thing about EdgeCT is that it's designed to protect systems that are not entirely in your control and assure that you can continue to operate through attacks, even though you're not in control of the entire system. So you just heard that the internet is not owned by governments. Well, that's true even when we in the Defense Department try to build networks across the world. We end up having to use commercial networks as a backbone for communication. And these commercial networks are much more susceptible to attack than our DoD networks. And so one of the things that we cannot guarantee is that those commercial networks are always available. So the EdgeCT program tries to make use of the fact that we have multiple vantage points with multiple service providers that connect to different edge networks within our system. And it uses these vantage points to do two things. One, to sense when commercial networks are under attack or under heavy load. And two, dynamically route traffic through different commercial networks through gateways that we own, edge gateways that we own, to optimally place traffic that's mission critical at different locations. Now, one of the things that the EdgeCT program has proven is that even when 80% of your commercial bandwidth is lost due to some kind of attack or some kind of bandwidth loss, we can still manage to push mission-critical communications through the network successfully. So these kinds of systems help us to ensure the commercial underpinnings of our communication networks. But there's other critical infrastructure we'd like to protect as well, that we'd like to be able to survive attacks. And increasingly, many of these systems are interconnected because they have control systems that use the internet at the end of the day to operate in a globally distributed way. One of the big systems that we worry about in our country is the power grid system. The power grid system fundamentally relies on communication to decide what it's going to do. And so when one part of the system is attacked, there are a number of second-order effects that can be caused. We can cause transformers to overload at the junctions between different power companies and different power grids. We can cause all sorts of cascade behaviors that are not anticipated from a single attack. And so we started a program last year called Radix. And the idea behind the Radix program is to couple automated situational awareness, automated detection of attacks, with automated monitoring of the electrical grid to, one, learn those attacks, and two, to better learn how to isolate the networks when they're under attack so that you can minimize damage. So this system is entirely automated, and the goal of the system is to do those things in a loop and to also discover novel cyber attacks through the signatures of changes in the electrical grid coupled with anomalies that happen in the cyberspace associated with the same event. Now, this program is designed to work on a wide distributed set of networks through observation points at each of the power stations. And it's already shown that it can do isolation much faster and much better than human beings can do. Now, what I'm going to leave you with at the end of this is where we think the direction of cyber is going to go in the future. So what I just showed you were a series of capabilities to do automated detection of attack and automated operations, automated mitigation of damage associated with attacks. But what we want to get to is a point where we can actually, once we've seen an attack, prevent other attacks of the same class from ever happening again. And so over the last couple of years, we've been running something called the Cyber Grand Challenge. And the idea behind the Cyber Grand Challenge is to essentially create a defense mechanism that's active and that will protect itself from a whole wide series of future attacks of the same class once it's seen a specific example. Now, we set this up as a competition, and the way that the competition goes is that each system has to protect a set of services, and it gets points, or it loses points, for allowing damage to happen to any of the services that it's protecting. This damage is caused by a series of attacks that are perpetuated against these systems in an automated fashion. So this particular challenge was a $4 million prize competition where the big prize was a $2 million effort for volunteers who would generate systems for us to evaluate during the Cyber Grand Challenge. Now, this is what Cyber Grand Challenge looks like. What you're seeing is live gameplay where all sorts of requests are coming into services, which are these little hexagons, hexagons underneath each system. And sometimes one of these requests or a couple of these requests are little red arrows hitting the system, and those are attacks. And in each round of the Cyber Grand Challenge, a different class of attacks is actuated against these systems. And the goal of these systems is to, one, be able to automatically detect the attack, two, mitigate the damage associated with the attack, and then three, patch the system autonomously, generate a patch via autonomous means so that that attack can't cause further damage on the system, while also accepting requests and continuing to process those requests successfully. So what I'm going to leave you with here is one of the great discoveries from this particular system. It was from a system developed by a bunch of students at UC Santa Barbara. Their system was called MechaFish, Mechanical Fish. And what you're seeing here, what you're going to see here in this video, is a system that manages to create a state machine patch against what's called the crack-adder attack. It's actually a fairly significant kind of attack because it's a stateful system that you actually have to defend against. And what you're going to see here is the execution of their patch versus the execution of the originally damaged code. They were able to patch this system automatically, no humans involved, within 80 seconds of the system generating the first bad input, getting the first bad input from an attack. Now, why I think this is interesting is that this system will eventually operate at very, very high machine speeds, right? Potentially at microsecond, millisecond range timeframes. And the fact that these guys were able to build this kind of defense is actually very, very interesting. This kind of patch took individuals years to find in the open. Just finding the bug itself took years in SendMail to actually find. And then the patch itself is complicated because the actual attack requires logic in order to be able to actuate. The system was able to deduce the logic and invert the process to create the appropriate patch, all automatically. Now, why this matters is that we think the future of this kind of cyber defense is going to be systems like this. Systems that can react at machine speed, systems that essentially build a form of cyber immunity, right? They detect attacks and then they build a way to defend against those attacks so that those attacks can never be actuated again in the future. All right, with that, I'm going to end and let you guys get to lunch. Hopefully you will enjoy the rest of your time here, and if you have any questions, please feel free to ask me. Thank you all.
Thank you.